Assalamualaikum and hi students. We have finished the central processing unit part. Now we are moving on to the next part, which is chapter 20, control unit. At the end of this chapter 20, students should be able to explain the concept of micro-operations. You have seen this in chapter 14 in fetch, interrupt, and also indirect cycle. Yeah, for example, at T1, the content of PC is supposed to go to MAR. In here, you're going to look at execute cycle micro operations. Second, students should be able to discuss how micro operations are organized to control a processor. What are the inputs? What are the output? And lastly, in subsection 3, you will understand hardwired control unit organization. Yeah, we have the microprogrammed way, but here we are looking at hardwired. Before we begin our discussion, let us see where we stand in terms of the structure of the computer. So in a computer, in a PC, we have I/O, we have memory, and we have CPU. And in the middle, we have system bus. You remember this, right? And then in CPU, okay, and CPU, we have subcomponent. So in CPU, we have ALU. We have, look at this, we have registers. We also have, look at this. And now, this is where chapter 20 is. We are going to look at control unit. Oh yeah, in the middle, what do we have? We have internal bus, which we have looked at when we learn about register and processor, and now CU. ALU is chapter 10. Register, we look at the previous before, chapter 14. Yeah, and also we look at the processor 14. And now here control unit is chapter 20. And the first thing we're going to look at is micro operations in 20.1. So what is the connection with control unit? It is the job of control unit to create the micro operations and instruct, yeah, what does each micro operation do and who gets to use it, how it goes into the CPU, and so on. So let's begin. To design a control unit, however, we need to break down the description further. In our discussion of pipelining in chapter 14, we began to see that further decomposition is possible. In fact, we have seen that each of the smaller cycles involve a series of steps, each of which involves the processor registers. Remember our right to left micro-operations, the symbol? So we have T1 and T2 is PC1 goes to PC. Yeah. We refer those steps as micro-operations. The prefix micro refers to the fact that each step is very simple and accomplish very little. Figure 20.1 in the next slide will explain this in detail. In this figure 20.1, it depicts the relationship among the various concepts we have been discussing. To summarize, the execution of a program consists of a sequential execution of instruction. So we have instruction cycle 1, instruction cycle 2, yeah, until instruction N. Each instruction then is executed during an instruction cycle made up of shorter subcycles. What are they, students? We just finished this in chapter 14. So we have fetch, and then maybe we have branching, then we go to indirect cycle. We must execute, and sometimes we have interrupt cycle. And the execution of each subcycle involves one or more shorter operations. Okay, remember back to chapter 14, we have RTL symbols. Yeah, so what are they? So let me give you an example of the fetch. If you remember, we have here we have PC. Yeah, the first micro operation goes to MAR. Yeah, at T1. And then we have the next micro operation, memory goes to MBR. Yeah, and then at the same time, yeah, but because it uses different unit, we have content of the PC, we add 1 and we send it into PC. So the first micro operation is at T0, and these two micro operations is at T2. Yeah, of course, then we have our T3, content of MBR goes to IR. So these steps is called micro operations. So fetch has 4 micro operations. They are functional or atomic operations of a processor. So the remainder of the chapter, we will show you how the concept of micro operations serves as a guide to the design of the control unit. The job of control unit is to produce these micro operations. So what rules should they follow? There are 2 simple rules. One is, please make sure that proper sequence is followed. Yeah, so you must make sure that PC goes to MAR, means send address first before you fetch the instruction. So you cannot have memory go to MBR, then only MAR goes to PC. Doesn't work that way. And secondly, please at all time avoid conflict. You cannot, for example, have read and write the same register at the same time. So that's why we have 3 time, yeah, T1, T2, T3. So if at that time memory is sending data to MBR, you cannot at the same time have the content of MBR to be pushed into IR. Yeah, that will produce conflicts. In chapter 14, we learned that fetch, indirect, and interrupt cycles are kind of simple and predictable. Each subcycle involves a small fixed sequence of micro operations. This is not the case for execute cycle, yeah? Because we know that to execute the instructions, it has so many instructions, right? CPU can do add, move, jump, store, load, loop, and so much more. And because of this variety of opcode, yeah, there will be a number of different sequence. Different opcodes will have different sequence of micro operations. It is the job of the control unit, to decode this instruction. So the control unit will examine the opcode carefully. Is it add? Is it jump? And for each different opcode, it will generate a sequence of micro operation based on what it wants to do. Does it want to add? Does it want to jump? And so on. To help you understand more, let us consider a hypothetical simple instruction. Add R1X. Yeah, X is a location in a memory. R1 is a register. So what it will do is it will add X into register R1 and save it inside R1. So for this add instruction, just for this add instruction, there is a specific micro operation sequence. So what they are, first, yeah, in the first step, the address portion of the instruction register is loaded into the MAR. Before that, why don't we draw that diagram of the register position? Okay, let's test my drawing. First, we have a pen. We have, what do we have up here? We have program counter, yeah, which will go into MAR. All right, and then we have buses. Okay, you guys familiar? What do you have? We have control bus, data bus, and address bus. And then it will go to, what are these? Memory. Right, and then we come back, and in here we have MBR and we have IR. Okay, kind of okay, right? All right, so then let's look again back at that instruction. So we need to look at the address portion of the instruction register. Please remember that we have finished fetch cycle. So when we have finished with fetch cycle, where we are right now, we are in IR. Yeah, we are in IR. In IR, there is an instruction. So that instruction at R1X is in IR. So we look at the address part of IR of the instruction. And we see that we need to go get X, which is in the memory. And let's assume that X is address 400 in memory, right? So where should, so the address portion of that IR, the 400 will be loaded into MAR, yeah? So IR, yeah, in the IR, and it goes to MAR, and then put it inside MAR. What do we put inside? That 100. Then the control unit. Okay, where is the control unit? The control unit is in the middle. The control unit will produce the read instruction. So we go to 400 here in memory address, and we found out that the value is, what do you want? What do you want the value to be? Okay, the value is 0, oh, you can't see it, 0003. So 003, and then we'll be inside data bus, and at T2, yeah, from memory, you will go into the content of 003, we'll go into MBR. So in MBR is the data 003. That is step 2. In step 3, finally, the content of R1. So you put 003, you add with R1, let's say inside R1 there's already 4, and then you will save it in R1, 7. So these are the micro operations for this kind of add. Even add has many. It can be add register, add register memory, add memory register, add memory memory, add memory immediate. So many. So for this one add R1X, these are the micro operations. So execute cycle is complex because different opcode of instruction will have different sequence of micro operations. We have seen that each phase of the instruction cycle can be decomposed into a sequence of elementary micro operations. Before we move on, I want students to remember back what is the phases of the instruction cycle. So we have fetch, we have indirect, then what? Execute, and lastly So fetch goes to indirect, indirect goes to execute, execute goes to interrupt, interrupt goes to fetch and execute. There's direct if there is no indirect and interrupt. So in our example, there is one sequence, yeah, standard sequence each for fetch, yeah, they have standard for fetch, for indirect, also for interrupt. However, for execute, yeah, one sequence for each opcode. So different opcode will produce different micro operation. So to complete the picture, we need to tie sequences of micro operations together, yeah, combine all four, and this is shown in figure 20.3. We are going to assume a new 2-bit register called ICC, Instruction Cycle Code. Here, yeah, ICC. The ICC designates the state of the processor in terms of which portion of the cycle it is in. Out of that 4, 0 is fetch, 0 1 is indirect, 1 0 is execute, 1 1 is interrupt. Those are the instruction cycle code ICC. At the end of each of the 4 cycles, the ICC is set appropriately. You know that indirect cycle is always followed by the fetch cycle. Yeah? So before indirect must be fetch. So let's try to trace this diagram and see how it works. So we always start from the ICC. So we're going, of course, we must start with fetch. So we go 0 0, we go to fetch instruction, and then there'll be a question. Is it a direct address? If it's direct address, yeah, so is it, okay, sorry, the question is it indirect? So if it's no, that means it is direct. Then if it's direct, we go straight to execute. So if you look up here, if it's not indirect, we just go to execute, right? And the ICC is 10 for execute. So if it is direct addressing, you go to execute. And then you must follow the arrow to the right. And you come up here again to ICC. Yeah? And then is it interrupt or fetch? You figure it out. Okay, go back to indirect addressing question here. Okay, if it is indirect, students know what to do, right? We need to go to indirect cycle. So ICC is 1. So either execute or indirect, you have to go back to, okay, follow this thing. So you must go back to ICC. So if after execute, you found out there's interrupt, then you will go to the left, right? So this is a very useful diagram to show you how the whole instruction cycle works. Of course, this is a simplified example. This flowchart for an actual processor would of course be more complex. In any case, we have reached to the point in our discussion here in which the operation of the processor is defined, yeah? Starting from, we have shown a few examples in chapter 14. So up until here, we have defined the performance of a sequence of micro operations. So from instruction cycle, you have sub-cycles. In each sub-cycle, you have many different micro operations. So we will now go to see how the control unit causes this sequence to occur. So what is the role of control unit in micro operations? (20.2) Control of the processor. As a result of our analysis in the preceding section, we have decomposed the behavior or functioning of the processor into elementary operations. What are they called? Correct, micro operations. By reducing the operation of the data processor to its most fundamental level, we are able to define exactly what it is that the control unit must cause to happen. Those functions that the control unit must perform is called functional requirements. This is the basis for the design and implementation of the control unit. So how do we characterize the control unit? By following this three-step process. First, we need to define the basic element of a processor. So who can tell me? What are the components that make up a processor? Anyone? Yeah, we have ALU, we have register, yes, we have bus, external and also internal, and finally we have control unit. Everyone got that? Next, we describe, the second step is we describe micro operations that the processor performs. Okay, this one, you know this by heart already. Yeah, the T1, T2, the RTL symbol. All these are micro operations. We have discussed 1 and 2. Now, in this subsection, we are more interested in knowing how to determine the functions that the control unit must perform to cause that micro operations to be performed. Yeah, it's not that difficult. You need to remember that control unit performs only two basic tasks. Yeah, two. Oops. There you go. They are sequencing and execution. In sequencing, the CU causes the processor to step through series of micro operations in the proper sequence based on the program being executed. While in execution, the CU causes each micro operation to be performed. In the next slide, we're going to look at the functional description of what the control unit does. The key to how the control unit operates is the use of control signals. The third step, to determine the function of what a control unit must do. So we have this block diagram, and then we figure out what are the input and what are the output of control unit. So first, we look at the input. The first input is down there, the clock. Do you see that, guys? Even control unit has a clock, so they can keep time. Do you keep time? Not yet, right? Because you're always late to my class. The CU causes one micro operation or maybe a set of simultaneous micro op to be performed for each clock pulse. Second is the one from instruction register, input into the control unit. These are the opcodes and addressing mode of the current instruction, which is used to determine which micro op to perform during the execute cycle. Then we have flags. You are familiar with flags. Yeah, they are needed to determine the status of the processor and the outcome of the previous ALU operation. Yeah, because the results of the operation will in turn will be put inside the flags register, and it determines whether overflow, whether zero happened, and the rest. And the last input is the control signals from the control bus. Yeah, it will provide signal to the control unit. So these are the input. Next, the outputs out of control unit. The first output is the control signals within the CPU. Within the CPU. Yeah. These are two types. First, those that cause data to be moved from one register to another. Within the processor, we have register, so between one register to another. And the second type are those that activate specific ALU functions. Yeah, so that is the first output. The second output is the control signals to control bus. All right, outside from control unit to control bus. So for this second output also, it has two types. First is the control signals to the memory, the one you always see in the fetch cycle and the other cycles. And the next type is the control signals to the I/O modules. We have discussed the control unit in terms of its input, output, and also functions. Now in 20.3, we are going to discuss control unit implementation. There are a wide variety of techniques that have been used. Most of these fall into one of these two categories. Hardwired implementation, oops, wrong pen, hardwired implementation, and microprogram implementation, the software. This one we will discuss in chapter 21. In chapter 20, we are going to look at hardwired implementation. In a hardwired implementation, the control unit is essentially a state machine circuit. Its input logic signals are transformed into a set of output logic signals, which are the control signals. So we're going to see this approach in this section. This looks familiar. Yep, this is a decoder. Hello, Digital Logic. All right, so what are they for? Yeah, what is the connection with control unit? So to handle the input and output of the control unit, so using a hardwired implementation, so you're going to use all those functions that you learn in chapter 6 of Digital Logic. So let us consider the IR, what is it? Instruction register. So the control unit make use of the opcode, okay, the first part opcode, add, load, yeah, store, and will perform different options. Yeah, so we'll issue a different combination of control signals for the different instruction. So to simplify this, for the control unit logic, there should be a unique logic input for each opcode. So what should we use? Yeah, the function can be performed by a decoder. So do you guys remember what a decoder does? Yep. Yeah, it takes an encoded input and produces a single output. So this might look a little different, but you can still understand it. For example, yeah, so if the input is 0001, yeah, so it will do output. Control unit will perform output 15. Yeah, if it's 1001, it will perform output 7. This is a simple one, yeah, for 4 binary input. Of course, a typical control unit will have a more complex decoder to account for variable length opcodes. This is another example of the hardwired implementation, yeah, a control unit logic. So we have a decoder also. Then we have a timing generator with the input clock, clocks, yeah, flags to the control unit. This is the end of chapter 20. To tie everything together, students must understand that the control unit controls the state of the instruction cycle, all the fetches, all the interrupts, executes, and indirect cycles. I hope students are able to appreciate that in a modern complex processor, the number of Boolean equations needed to define the control unit is very large. The task of implementing a combinatorial circuit that satisfies all of these equations becomes extremely difficult. You know that, right? From digital logic, hardwired, it's difficult because you have all those wiring, and then do we go here? Do we duplicate this? Yeah. So the result is that for a far simpler approach, we're gonna go the micro programming way. Yeah. So this is the topic for the next chapter 21. Bye.